Bismillahirrahmanirrahim. Assalamu alaikum everyone. We are going to conduct another video tutorial on signal and system course. Uh, Recently, we have completed an important section of signal and systems course, which was about transformation of time-dependent variable, in which we performed various time operations, including scaling, time reversal, and time shifting. Now we are coming back to the types of the signals. Before the section of time-dependent variables transformation, uh, we were covering the types of signals, and now we are coming back to that section. Uh, we have covered various types of signals, including discrete time, continuous time signal, periodic signal, aperiodic signal, and many other type of signals. But we haven't covered these signals, which we are going to cover, which are even and odd signals. So in this lecture, we are starting even and odd signals. Actually, to understand briefly or to understand accurately or the right concept of even and odd signals require the knowledge of time operation, specifically time reversal operation, right? So that is why I did not cover these types of signals earlier. So I'm going to cover some more type of signals, including even and odd signals, so that we can actually complete the set of all types of signals, or the basic all types of signals, uh, which will be very helpful in the analysis of signal and system course and many other tools which we are going to learn in this course, right? So let's start even and odd signals. So in this video, we are starting even and odd signals, but we cannot conclude this complete topic in a small video. We will be covering only even signal. So let's start with even signals. So what are even signals? Even signal is the signal which must satisfy the following condition or the following mathematical relation, and that relation is what? This one: x of t equals to x of minus t. This is a very important mathematical relationship, and I hope that everybody knows it now, that what does mean by x of minus t, because x of minus t is time reverse version of x of t actually, right? So if I would have covered this signal earlier, when we did not cover the time transformation or time dependent variable transformation, or independent variable transformation topic, this thing could be very difficult to understand. But now we know that what this relation means. X of t means the original time domain signal should be equal to the time reversal version of itself, right? So what is time reversal? We know that, for example, we are given this signal. Let's say this signal 0 to, let's say, 2. This is a signal and its value is 1. Its amplitude is 1 here, right? So if I want to make its time reversal version or time reverse it, what is going to happen? I will flip this signal across the y-axis or across the origin. So this signal will become from -2 to 0, and amplitude won't affect, right? But the effect will be appearing in the time domain. So that means if I take a signal x of t, so that was basically x of t, and I made it a reversal, which is x of minus t. And if I compare them, if they both are equal, that means the signal was, the original signal was a even signal. So we can classify that signal as an even signal. So do you think this equation actually appears to be effective in this case? No. If you see clearly that this signal starts from 0 to 2, the original signal, its amplitude is 1, but when we reverse it or time reverse it, it becomes from -2 to 0. So both are not equal. One of the signal is present, for example, the total duration is from -2 to 2. So the original signal is present in 0 to 2, and the other part of the signal or the time reversal signal is present from -2 to 0. which means both of them are not equal. So this signal is not an example of even signal. I hope you understand this point. Let me take one more example. Okay, let's take one more example. And in this example, I've taken another simple signal, but this time signal's duration is from -2 to 2. So this is again a square pulse, you can say that, or a rectangular wave, or rectangular pulse, sorry, not wave. So signals values or the appears signal values start to appear at -2. So t equal to -2 signal starts and its value becomes this one. Let's say this amplitude is around 1. I'm just taking simple values so that you can easily understand the concept, right? So signal starts from t equals to -2 and goes to t equals to +2. So that means signal remain 1 till t equals to 2. So if I'm going to time reverse it, how it will look like, let me time reverse it for you. So this is the time reversal version of original signal. And if you see and observe them clearly, so there is no difference at all. Both of them are equal because signal also starts from -2 and goes to +2. So that means your original signal is exactly equal to the replica version of itself or the time reversal version of itself. And that means I want to add something here. You cannot only test the signal as a whole, you can actually test it on the simple individual values. For example, let's say I'm gonna use this signal x of 3, right? So what is the value of x of 3 in this signal, right? So we know that there is nothing value present here, so x of 3 is what? 0. And if I am going to test the same thing over here in this signal, x of 3, right? If I'm going to put here 3 in this signal, so you can say that 3 will be somewhere here and there is nothing. So that means this is also 0. Similarly, if I want to test what, so if I conclude it, that means x of 3, right? Uh, okay, so that means the value of x of t at 3 is equals to the value of x of minus t at 3, right? That means this equation is being satisfied, right? So what does it mean? It means that x of t at t equals to 3 is exactly equals to x of minus t at t equals to 3, right? Similarly, you can check for another value. For example, you can check at 0 point, its value is what? 1. At 0 point, its value is also 1, right? At 2, its value is 1. At 2, its value is also 1. That means this complete signal is basically equal to its time reversal version, and that means this signal is an even signal. And this is the basic definition of even signal. I hope you understand it. You can take many more examples and to specify it. So if any signal you want to test whether it is an even signal or not, you need to just take its time reversal and calculate its different and compare their values at different positions. So far, I've taken two examples to verify what is the concept of even signal and how one can check whether the signal is even or not. But in both examples, I took a graphical example, which was more easy to understand. But now I'm going to take a mathematical relation or mathematical example of x of t, and we will verify whether the signal is x of t or not, right? So let's take one mathematical example and then we will conclude this video on even signals. Okay, so this is a mathematical example of even signal. So this signal is x of t, and I've also transformed it into time reversal version. So this is x of minus t, right? This is x of minus t, and this is x of t. And I'm going to test this equation on this signal, whether this relationship actually exists for this signal or not, right? So I need to compare x of t with x of minus t, and if both of them are equal, that means this relationship would be valid and this will be an example of even signal, otherwise it won't be, right? So let's say we understand that the signal start from this equation. We can say that values start from -2 to 1, So that means, let's say I want to calculate x of -2. So what will be its value? Its value will be what? 3 here. Let's say I'm going to test here the value of x of -2 in this equation. So is -2 exist in this interval? No, that means this definition, which is equals to 3, is not valid for two position. Rather, the signal's value at -2 would be simply 0. So you can simply check that at very first point, at very first point, this signal fails to fulfill this equation, right, at which we are testing. One may have started, let's say, at x equals to 1, right? So if I'm going to test at x equals to 1 or t equals to 1, so 1 exists here, so that means x of 1 would be 3. And similarly, 1 is also exist here, so x of 1 would be 3 here. So you can see that at some point, this signal actually validates this relationship, but this is not true for complete signal. That is why this is not an even signal, right? So this signal is not an even signal. You can simply tell it by mathematical values, or by comparing to mathematical definitions of x of t and its transform version, or the time reversal version of x of t. It's okay. It is another example in mathematical terms. So I'm taking example of x of t equals to t square, and I've also shown here x of minus t. So basically just minus t was replaced with minus t. So minus t whole square will become again t square. This time one difference is there compared to the previous mathematical example, that there was some interval defined, but we don't see any interval defined. So this is an simplified or simply defined signal. So it is defined for complete domain from minus infinity to plus infinity. That is something which is not present in the last example. So this is also, you can say, one mathematical example of complete lasting signal. So this signal is defined from minus infinity to plus infinity. Okay, let's test this signal now. Okay, let's test this signal now for, okay, that was something that I wanted to explain because it was different from the previous example. But now we are going to do again the same check. That means we are going to verify this equation on this signal. So let's say I'm going to test the value of the signal at 4. So x of 4, if I'm going to put here 4, it will be equal to 16, 4 square 16. And similarly, if I'm going to test here x of 4, so it will be 4 square would be simply 16. Similarly, you can test for another value. Let's say I'm going to test it for minus 3. So minus 3 square would be 9. And similarly, if I'm going to test the signal for x of minus 3, so minus 3 square would be 9. So this equation is valid for complete domain. You can test it for any other value because this is it is a square signal, and a square will be equal. Either you take negative values or positive value. Okay, I want to add one more fact here. In normally literature, in books, or in journal video tutorials, you normally found that even signal is a signal in which the positive index values are equal to the negative index value. That means x of minus 3 would be equal to x of 3, or x of minus 5 would be equal to x of 5. Right? So normally they actually explain the even signal like that as well. And this fact that positive index or positive index values are equal to the negative index values is the result of this important relationship, which I explained you guys mathematically and graphically, that whenever a signal is equal to same, whenever a signal is exactly same as its time reverse version, so that means that signal is a time reversal fact, and that particular relationship actually dictates this specific relation as well, that positive indexes are equal to the negative indexes. So I hope whenever you go across other video tutorials or go various other literature, so you may find this definition as well. So I just wanted to add this definition as well. So positive indexes are equal to negative indexes. Whenever this signal, whenever this property is present in any signal, that signal will also known as even signal. Okay, I want to explain a trick here that you can actually apply in graph of the signal. And using that technique or trick, you can simply tell anyone whether this specific signal is even or not, right? So this is an even signal. You can see that by comparing the values, whatever the value present at -3, it is also present at 3. Similarly, you can also compare the value at 2, or you can also compare the value at -2, right? So both of them are equal. That was a way to check whether this is an even signal, but I want to verify it without verifying the value. So what I have to do, I have to flip this signal across the y-axis, or fold this signal across the y-axis. So this part which is present before y-axis will remain same, and the part which was present in the positive x-axis, if you just fold it up, it will completely overlap this signal. So after folding the signal will completely overlap. So if you just fold the signal across the y-axis, or you can actually fold negative values over positive, so your signal will look like something like that, right? So you can fold it in both ways. Either you fold the negative values over positive values, or you fold the positive values over negative values. So your signal will be complete overlap. And if this complete overlap is present, that means your signal is even. So this is a trick by which you can simply identify the signal is even or not in a graphical domain, right? So you can take one more example. Let's say I'm gonna take this example. So you see that this area is short and this area is greater or longer. So if I flip, the positive domain area will remain same, but if I flip this negative area, so it will come up here. So this is the folded area. And you see they are not completely overlapped. So that means this signal is not even signal, right? So this is the simplest trick by which you can simply identify whether the signal is even or not in graphical domain. Okay, so that's it that I wanted to tell you guys about even signal, how one can identify what are their mathematical relationship, how you can check it in mathematical domain, how you can check it in graphical domain, what are the tricks, and all the things we have done in continuous time domain. And I want to just add one last thing, that this is also valid for discrete time domain. So the equation, this will be the equation, right? So this equation is for discrete time signal. So whatever the signal value, discrete time signal value, it will be equal to the time reversal version of discrete time signal. If both of them are equal, that means that discrete time signal is also even signal. So all the tricks, all the discussion which we did in graphical domain, in mathematical domain, is also valid for discrete time signal. So even signal can also be continuous time and in discrete time, and you need to just verify these equations. If you're gonna work on continuous time signal, you need to check this equation. If you gonna work on discrete time signal, so you need to check this equation. So I hope you have understand about even signal, everything, the mathematical relation in continuous time, in discrete time, in mathematical representation, how one can verify the signal is even or not, in graphical representation. So in this lecture, we covered each and everything about even signal. The next part, which is odd signals or odd signal and how they are different from it, we are going to cover in next video tutorial. So in this lecture, if you have any query, you can post your queries in comment section. Thank you so much for listening.